My name is Michael. I'm author of AWS in Action, published by Manning, and I'm also writing a blog about AWS called cloudonaut.io. Today, I want to talk about evolutionary serverless architectures, and I'm using an example, which is a chatbot that I created 2 years before, and it was basically developed during a hackathon, and now it's a product that people use and pay for. So in 2016, AWS announced the Slackbot competition or something like this, where you're basically, the limitation was that you have to use the Slack API and it must run on AWS. So that was the limitations that were set. And in October, they announced the winners, and our chatbot was one of the winners. And today, we have a few users using our chatbot and also a few users paying for the chatbot. We had to make a few changes to reflect this. And what I had in mind when doing all this is a book called Building Evolutionary Architectures. And this is highly recommended by me. And they define an evolutionary architecture as something that changes incrementally and where fitness functions are used to make sure that things evolve in a good way. So like in nature, if things evolve, then usually it evolves in a way that improves the system, because otherwise they just die, and if they get better than the other ones, then they will survive. And that's the same principle here. And finally, evolutionary architectures also try to accomplish appropriate coupling, and we will see how this works in a real example. So that's the chatbot that we created. It's called Marwood. And it's basically a Slack bot that supports your DevOps team to detect and also solve incidents on AWS. So why should you use Marwood? First, it has a smart escalation algorithm that minimizes distraction of your team while still tries to keep the response time low. Second, that configures AWS for you to send all the monitoring data to Marwood. It's fun and easy to use. And finally, it provides you contextual help to resolve the incidents, because Marwood knows a lot about how AWS works. So this is how it looks like. So basically, you get a message in Slack, and then we basically tell you what happened, and also there are some links right into the AWS management console to get more details or also to resolve the problem. So in this case, your database has failed over to the standby machine. So your application may need to reconnect to the database, but we basically understand all kinds of problems in AWS. So what is the fitness function? So that's really important, because if we want to evolve our architecture, we have to know, and we also have to ensure that we evolve it in a way that is better than the architecture that we had before, because otherwise it doesn't make a lot of sense. So basically a fitness function produces, by looking at something, so for example, your architecture or parts of your architecture, and it produces a figure of merit. So this is kind of a figure that describes if the state of the thing, in what state it is, and then you try to optimize to make this number better. So a few examples. What are key fitness functions of Marwood? So the most important thing for us is we never want to lose an alert. So if you send an incident to us, we should never lose this. So we accept the alert, and then we forward it to Slack. We want to have, so as we learned that, like, you expect the chatbot to respond quite within a few hundred milliseconds. So one of our fitness functions is that the end user latency should be below 200 milliseconds to respond fast if you talk to our chatbot. Another fitness function that we use, and that's very easy to track automatically, is that our code coverage should be above 80%. That's also a fitness function that you can use. As we also heard after lunch, is that you should monitoring all the things on AWS with, for example, CloudWatch alarms. So our monitoring coverage should be above 90%. So everything that we use should be monitored for like error counts or latency or things like this. And finally, also something that we wanted to have as a fitness function is that we want to prefer managed services over self-managed stuff. So when we evolve our architecture, we make sure that we will use more managed stuff while we evolve the architecture. Okay, so how does the architecture look like? Who is familiar with cloud graph diagrams? Okay, so basically, we start at the bottom, where we have the API gateway. So Slack sends us messages like events or webhooks. And also, our users send us, for example, CloudWatch alarms using an SNS topic. And then, in the first version of our architecture, we had a single Lambda function behind the API gateway that received all the requests, then looked up some data on DynamoDB. We also sent some stuff to Kinesis, where we run Kinesis analytics for weekly, like we have a weekly report, how many alerts you have received, how long it takes until you resolve them, and stuff like this. We also report some business metrics to CloudWatch, like how many people signed up, how many alerts were created, and stuff like this. And of course, we also talk to the Slack API a lot. And one thing that we needed that was not available out of the box was a kind of a timer infrastructure. So when we escalate an alert to you, we wait for 5 minutes. If you don't respond within 5 minutes, then we escalate this alert to the next user. So we need something to check after 5 minutes if you have acknowledged the alert or not. So what we did is we used a SQS message queue, and we send a message to the queue, and you can say to the message, it should only appear in the queue after a certain amount of time. Since there's no native integration to SQS at the moment, we had our own Lambda function polling the queue. And this comes with a problem because you can only poll like with a CloudWatch event, you can only poll once a minute, so you have kind of a delay from the messages available in the queue until you process them. So this was a problem for us. Another problem was the Slack API waits for exactly 2 seconds. So you have to respond within 2 seconds, or Slack will basically stop listening for your answer. And with this architecture, we run into problems because we had to make quite a few calls to Slack in some cases, so we were not able to respond within 2 seconds. So that's a problem of this architecture. And the other problem was that this timer kind of thing is kind of slow because it only checks every 60 seconds. Okay, so if you apply the fitness functions to this architecture, there are some situations where we lose alerts because Slack only waits for 2 seconds, and depending on how far we were while processing this request, it could be that we just missed the alert. Also, end-user latency was very, very often well above 200 milliseconds, like 5 seconds and 10 seconds and higher. But still, we achieved good code coverage, our monitoring coverage was good, and we also had only managed services in the architecture. So this is how the architecture looked a few months after our initial try. So I call this version 2, but this doesn't mean that we basically switched from version 1 to version 2 in one shot. So this was incremental. So it took many, many steps until we reached version 2 of the architecture. As you can see, it gets a little bit more complicated, but still it's not completely completely complex. So we still have the API gateway at the beginning. We have some more sources that send alerts to us, but that doesn't matter too much. But basically, the biggest improvement is here that we added a Kinesis stream between receiving something and actually processing it. So now we basically respond. So as soon as the message is in Kinesis, we respond to Slack, okay, fine, we are working on it, and there's some like processing indicator in your Slack client. And then we try as fast as possible to process the message and then update the message in Slack. So that's one of the major improvements. We also added X-ray here because it was very hard for us to see where we spend so much time because we had no X-ray before. So now we have X-ray to track what's going on inside our system. So by adding the Kinesis stream into the architecture, we run into a problem because if the Lambda function fails while processing the message, it basically retries, which is one of the big advantages that you get when using Kinesis. But it's also a problem if your function is not implemented in an idempotent way. So we basically ended up with creating the same alert multiple times and things like this. So this was a problem that we hadn't had before because we basically don't had retries before. But now we have retries, and now we have to deal with this. The second problem was that our CloudFormation template, it was managed before by serverless framework, and then we switched to SAM, but this basically doesn't matter too much here. But we hit the 200 resource limitation. Because we have so many CloudWatch alarms, like 2 CloudWatch alarms for every Lambda function, for every DynamoDB table, I think you need at least 3. So one for throttles, one for read and write capacity exceeds. Then you have indexes where you need the same amount of alerts, and then you have like 10 tables, and then this really grows and grows and grows, and sooner or later you have more than 200 resources, and CloudFormation just stops to deploy your stack, and then you are in troubles. Another problem was that still not everything was kind of moved through Kinesis, so we still had high latency for some of our actions. So when we reevaluate the key fitness functions, the situation improved a little bit because for most of the calls we improved end-user latency by adding Kinesis, but still it's not perfect. In some situations we are still slower than 200 milliseconds. So let's look at how the architecture looks today. So what changed is that basically everything now sends or is processed asynchronously. So we just push a message into Kinesis and then process this in the background. So we can, with a very high chance, respond within 200 milliseconds. We also use DynamoDB streams for all kinds of analytic stuff that we do. For example, creating these business metrics like sign-ups and alerts created that we push to CloudWatch alerts. So we just put the item into DynamoDB, and then there from the DynamoDB stream, at some point of time, we then push it to CloudWatch as well. So another improvement here is that we looked into step functions, which is a service to orchestrate Lambda functions on AWS. And it has a nice feature because it can wait for a certain amount of time with second resolution. So we replaced our SQS solution with a step function. So now we have like 1 second accuracy for our timers, which is great. Another great advantage is you don't pay for the wait time in step functions. So it's also like cheaper, which doesn't matter to us because it's not a lot of traffic in our system, but it's still nice. And we also replaced our analytics part with step functions to get rid of Kinesis analytics, which also too costly for our use case. So when we reevaluate our key fitness functions, we now basically improved the end-user latency as well, and now the architecture is kind of in a green state, so we are very happy with it, and we don't know how to optimize it at the moment. One thing that I forgot is we also separated those things out into separate CloudFormation stacks, so we then kind of no longer have the problem of the 200 resources limitations for the whole thing because we just have multiple stacks now, so it's not a problem for us anymore. Okay, so a short summary. When you start, or at least that's what we experienced, when you start with a serverless project, you should really start as simple as possible, which means don't optimize at the beginning. So that's basically the most important thing. Automate your deployment. So for example, use the serverless framework, use like CloudFormation SAM, or whatever you want to use, but use something to automate the deployment. And then use small building blocks. I mean, you are on the serverless conference, so you probably want to use something like Lambda, so it's a small building block already, so that's fine. And then what's also important, add monitoring and tracing everywhere, because you need this data later to optimize the system. So once the simple solution is out there and you have some users using it, they generate data, so you actually can analyze the monitoring and tracking data, so you see in which situations the system is slow or where errors are more likely than in other parts, and you can improve those parts. So you basically optimize the system at the points where it's necessary. And finally, it's also a good practice to decouple your system a little bit, and we experienced that it's really easy to decouple the system with step functions, so you can move a lot of like logic out of your system by creating a new step function or a state machine in step functions, and then you just call the interface of the step function, and then everything else behind this is kind of decoupled from the rest of the system. Other learnings, step functions are really great for like timed processes because they sleep for like, you can sleep up to 1 year, I think. So even if you have like really slow going stuff, it's a good fit. One problem that we encountered is that in some situations we wait for user input in a step function, and that's not really possible at the moment. You can, for example, poll a DynamoDB table every second or something like this to see if the user clicked, but it's not possible to directly let the user interact with a step function. It's very important to have idempotent state transitions in your system. So if you use something like Lambda, which is like distributed system where it is possible that the function is executed multiple times, even you only called it once, that's really important. Otherwise, you will end up with like multiple entries in your database. And finally, if you make remote calls, for example, we call the Slack API quite heavily, you definitely need retry logic because, for example, in the Slack API case, so that's down at least once a week. So you have to retry and also retry like a few minutes later until it's successful. And with Kinesis, that's really easy as long as you have idempotent implementations of your functions. That's it. The slide template was provided by Slide Carnival. The photographs were provided by Pexels. And last but not least, check out Marwood if you run on AWS and need some more monitoring. Thanks.